remember last time by last time I mean yesterday, which feels crazy. We left off talking about inverse functions, and we were about to start talking about logarithms. We just didn't quite get there.
I've got a question about WebDesign. I see for your new class, click the enroll yourself link, and then it takes you to the class enroll search page. And
yeah,
I can find where it says the course and the name and all of that stuff. But when I click confirm to register, it'll load, and then it will say something happened, but I still can't access the class on WebDesign.
That's weird. Let me check my WebAssign roster real quick. Let's see. Let me sign into WebAssign here. Roster. I have you in my WebAssign roster.
All right.
So you shouldn't have to register anymore. Try logging in.
All right. I've closed out of it, and I'll log back in.
Yeah, because it says that you're well. Let me see what this says. You're in my roster, but it says you're not registered. I'm not sure what that means. I'm not sure if that means that you haven't purchased the WebAssign key yet.
All right.
Because that could be what that means.
Let me check. Well, I can now see where it's talking about the class. Do I trial? I think it does mean that I have not yet bought it. Let me see if it'll take me to where I can.
Okay.
Because when I'll click on that and it just takes me back to where I'm not enlisted in the courses. It doesn't take me where I can buy it. It does say view trial access.
That's odd. Do you have any ad blocker or anything on your browser?
So it's 4-month access. Is that what it is?
What was that? Yeah, the 4-month access. Yeah.
All right.
Yeah, and I do apologize for us using a paid resource this semester. We're moving to this class being using free resources in the future, but since we are also shifting to 7.5-week courses, some of us were reluctant to change the course material and change the course structure at the same time.
All right. Yeah, I think I've figured that out now.
Awesome. So let me go ahead and share my Microsoft OneNote here. So today we're going to pick back up where we left off. We left off talking about inverse functions. And we very quickly started talking about how do I find the inverse of... Oh, is it not here? Oh, yeah. How do I find the inverse of this thing? How do I find the inverse of an exponential function? And the answer to that is we just defined there to be an inverse, basically. So exponential functions. So let me make sure that my thing here. There we go. Oh yeah, can you mute, by the way?
Oh, yeah, sorry.
So exponential functions are 1-to-1, right? Yes, I am recording now. Thank you. Good call. I'm recording now. We're recording from the beginning today. We got it. So the idea here is if I have some generic exponential function say f of x equals b to the x. An exponential function is always 1-to-1. Do we agree? If we were to graph this, we would never have any repeated y values, right? These things are like, whoop, sorry, that was a bit of a bad illustration. Maybe like this, or like this, right? Kind of like this. My drawings are poor. Please forgive me. If we were to graph these, we would get something like this, right? We've seen exponential functions in the past. So I can confirm that these are 1-to-1. These pass the horizontal line test. So that means that they have an inverse. Now the inverse of this is difficult to find just by doing some algebra, right? We attempted to do it, but we didn't quite have the tools to do it because we have to define a special function. And this function is called the logarithm, the logarithmic function. So let me just copy and paste a nice little definition here. If b is greater than 0 and b is not 1, the exponential function f of x equals b to the x is either increasing or decreasing on its entire domain. And so it's 1-to-1 by the horizontal line test. Therefore, it has an inverse function, which is called the logarithmic function with base b, and is denoted by log base b. If we use the formulation of an inverse function, f inverse of x is equal to y, which implies both ways that f of y is equal to x, then we get log base b of x is equal to y if and only if b to the y power is equal to x. So this means that log base b of x is the exponent to which we have to raise b to get x. Does that make sense? The answer to this, right, whenever we evaluate it, log base b of x is the exponent to which b must be raised to get x. For instance, and this only works if x is greater than 0, but that's kind of trivial because the logarithm can only take values that are strictly greater than 0. For instance, log base 10, this is the natural logarithm, which actually means I don't even need to write the base. I can just write log, but we'll write the base in this case. Log base 10 of 0.001 equals -3. This is because 10 to the -3rd is equal to 0.001. So -3 is the power that you have to raise 10 to in order to get 0.001. Does that make sense? This is how the logarithm is defined. It does? Good. Let me do something real quick. I have these Logitech speakers, and they're breathing through different colors, and I don't like that. Okay, there we go. There we go. They're just one solid color now. That's what I wanted. Actually, even better, I'll just turn them off. I'll just turn off the color cycling. It was getting distracting watching them go from like red to green, etc. So we had some cancellation equations for inverses, at least what the textbook calls cancellation equations. which are these. Let's copy and paste these so we can reference them. F inverse of f of x is equal to x, and f of f inverse of x is equal to x, right? So we said that if f of x is b to the x, then f inverse of x is log base b of x, right? This is how we defined our logarithm, right? Logarithm with base b is the inverse function of an exponential function with an exponential base of b. So then, f inverse of f of x is f inverse of b to the x, which is log base b of b to the x. And from this equation, f inverse of f of x is equal to x. Does that make sense?
Yes, it does.
And this is going to be true for every x value that's in the domain of this inner function. The domain of b to the x is all real numbers. So this is true for every x that is an element of the real numbers. This is true for every x that's in the real numbers. Similarly, f of f inverse of x is equal to f of log base b of x. And this is equal to b to the power of log base b of x. And this is equal to x from this second equation. Do we agree with this? Yes. And this is going to be true for every x value in the domain of this logarithm. The domain of a logarithmic function is going to be anything that any input. Let me rephrase here. I can input anything into a logarithm that causes the argument of the logarithm to be greater than 0. So this is for every x greater than 0 in this case. I cannot input 0 into a logarithm. And that's because you can never raise something to a power and get 0 as your answer. Does that make sense? Right? Because if I were to ask, so if I were to say, what's the log of 0, right? This is asking, now if I don't see a base here, the base is implied to be 10. This is called the common logarithm. This is asking me, what power do I have to raise 10 to in order to get 0? Well, there's nothing I can raise 10 to in order to get 0, is there? There's no power that exists. Similarly, if I were to plug -1 into a logarithm or any other negative number, can I ever raise a positive number to a power and get a negative number as my result? No. So logarithms are not defined for negative inputs either. Logarithms are only defined for strictly positive numbers. So because logarithms are inverses of exponential functions, the logarithmic function log base b of x has domain. Well, we just stated the domain. 0 to infinity, not including 0. And it has a range of all real numbers. And this should make sense because the domain of b to the x, so if I have, so let's say f of x equals this, f of x equals this, the domain of b to the x is all real numbers, and the range of b to the x is 0 to infinity. Do we agree with this? And I obtain an inverse of a function by swapping its domain and range, right? So notice here that between my logarithm and my exponential function, my domain and my range are swapped, as they should be, right? Let's take a peek at graphs of logarithms real quick. Let me just take a snippet of these graphs of these logarithmic functions. And the graph of a logarithm is the graph of an exponential function reflected across the line y equals x, right? That's how we find the graph of an inverse of a function. Notice here that all of these seem to be passing through a common point, right? All of these logarithms that you see here are passing through the point 1, 0. This is because log base b of 1, well, log base b of 1 is equal to 0. Because any number raised to the 0th power is 1. Does that make sense? So log base b of 1. So log base b of 1 is 0 because b to the 0th power is always 1. Any number to the 0th power is 1. Does that make sense? So basically, all of these properties of logarithms are going to follow from properties of exponential functions that we've already discussed, and from properties of exponents. In fact, let me go over here and copy and paste these exponent laws so we can compare. These are 4 exponent laws we discussed. And here are some logarithm laws. If x and y are positive numbers, then log base b of xy is log base b of x plus log base b of y. In other words, if I have multiplication inside of a logarithm, I'm allowed to express this as the sum of 2 logarithms with x and y as the arguments of those logarithms. Similarly, if I have division inside of a logarithm, I'm allowed to express this as a difference of 2 logarithms, and vice versa. I'm allowed to express a difference of 2 logarithms as the as a quotient inside of one logarithm. And log base b of x to the r is r times log base b of x. So if I have an exponent inside of a logarithm, I'm allowed to pull that exponent in front of the logarithm as a constant multiple of the logarithm. Notice how these seem to be related to these exponent rules. This one, this one, and then which one here? Maybe this one. These first three. Yeah. 4. Let's see. When you raise an exponent to an exponent, you multiply the exponents. So this correspondence between exponentiation and multiplication, I think this one here. I think probably 3. Yeah, I'll just make this larger. Boom. Does that work? There we go. So the basic idea of laws of logarithms here, the way that this makes sense in my brain, and this could be different for your brains as we have different brains, right? Fortunately for you, at least, we have different brains. So the way that I think about this is a logarithm can take these operations, such as multiplication or division or exponentiation, and reduce them in strength by 1 level, essentially. So this takes multiplication and reduces it to addition. This takes division and reduces it to subtraction. And it takes exponentiation and reduces it to multiplication. Does that make sense? I think of this as reducing the strength of the operation by 1. Multiplication is just repeated addition, right? And because multiplication and division are inverse operations, and addition and subtraction are inverse operations, I think of division and subtraction as analogous. So whenever I think of reducing the strength of division by 1 level, I think of reducing division to subtraction. And because exponentiation is repeated multiplication, exponentiation is 1 level more powerful or stronger than multiplication in my brain. I hope that makes sense. And honestly, that's actually the historical impetus for discovering this thing that became known as the logarithm. Historically, the reason for wanting to seek out something like this was it would be really nice if we could take these complex problems involving multiplication and turn them into problems involving addition, right? Because addition is way easier than multiplication, right? So if I could just figure out a way to turn a multiplication problem into addition, that would be awesome. That was the whole idea of logarithms. All right, let's move on here. Let's use the laws of logarithms briefly and swiftly. Use the laws of logarithms to evaluate log base 2 of 80 minus log base 2 of 5. So on their own, these logarithms would be very difficult to evaluate, right? Now, you could potentially type this into a calculator and you'd get some answer. Or what they used to do is they used to publish books with values of logarithms in them. Like huge tomes with just filled with values of logarithms. You don't need that anymore, right? You could conceivably look these up in there. But the easiest way of doing this is to combine this using our logarithm laws. I see that if I'm subtracting two logarithms, and a very important thing is the logarithms have to have the same base. Notice these both have base b in our logarithm laws. They have to have the same base. So we have to check, do these have the same base? Yes, they both have base 2. So I'm allowed to combine them. In this way, I have subtraction, so I'm allowed to turn this into division inside of one logarithm. So this is log base 2 of 80 divided by 5. 80 divided by 5 is 16. And now this is asking me the question, 2 to what power is 16? 2 raised to what power is 16? 4. Yep. Fast. Yeah. Some of us have been doing our powers of 2 in our heads while we're trying to fall asleep, haven't we? That's what I do. But it never ends up working, and I always get way too high in the numbers. You dreamed calculus last night? You'll be dreaming calculus for the rest of the semester, and possibly the rest of your life. Now that's not supposed to sound like a threat. Now, a lot of the time, the most convenient choice for the base of a logarithm is going to be Euler's number, E. This logarithm has a special name. In fact, in calculus, and most of the time, this is just going to be the most convenient logarithm to use. Log base b, or log base e of x is denoted ln x. Ln is Latin. It's logarithmus naturale. So this denotes the natural logarithm. Well, the natural logarithm is the inverse of the exponential function e to the x, right? This means that natural log of e to the x is x for all x that are in the real numbers, and that e to the power of natural log of x is equal to x for all x greater than 0. Does this make sense? We also have that natural log of e as a result is 1, because this is asking the question, e to what power is equal to e? Well, e to the first power is equal to itself, right? How do we feel about all of this so far? Pretty good. Let's work out this problem real quick. And pretty soon we're going to be moving on to 2.1, wherein we will begin calculizing. We will begin using actual calculus, kind of. We'll begin laying the foundations of calculus. Oh, I didn't capture all of the question I wanted to. Solve this equation. E to the 5 minus 3x is equal to 10. How can I solve this exponential equation? How can I solve this for x?
You could start by taking the natural log.
Yep, take the natural log of both sides. Very good. So we want to take the natural log of both sides of this equation. If I only have one thing in the argument, then it's fine to write this without parentheses. It's going to be the same with the trigonometric functions. If you only have one thing in the argument, it's fine to drop the parentheses. Natural log of e to some power just yields that power, right? Because these things are inverse functions. That's why we chose natural log. And now this is pretty straightforward to solve. This is just an algebra problem, right? We can, I don't know, what's the best way to do this? Maybe add 3x to both sides, subtract natural log of 10 from both sides. We end up with 3x equals 5 minus natural log of 10. Divide both sides by 3 and we get x is equal to 5 minus natural log of 10. I'll write it in parentheses since we're going to throw all of this stuff over a 3. This is an exact answer. If you're asked for an exact answer to this problem, then this is your answer. We could approximate this in a calculator, but if, for instance, WebAssign asks for an exact answer, you need to enter this answer. If you enter a decimal answer when you're asked for an exact answer, then your answer is wrong. And that's not being picky. That's just you're wrong, right? not to be harsh. So we could approximate this if we wanted to. This would be about 0.8991 in a calculator. Let's quickly use some, yes, question.
Are most functions like this an infinite decimal, or are they just incredibly long?
Wait, what was that?
Are most problems like this a repeating decimal, or are they just very long? Or why the decimal can't be the exact answer?
This is not a repeating decimal. This is going to be an irrational number. It's going to be a non-algebraic irrational number, more than likely. This is probably going to be a transcendental number.
All right, thank you.
Yeah, no problem. Jakira.
Okay, so when I was doing the homework last night, because I still went ahead and done it, when it came to, because I done the number 11, that was just like this problem, but when I divided it by 4, I got 2/4, but the answer was 1/4, and I was just confused on how it was 1/4.
Number 11 on the number 11 on the 1.3 to 1.5 homework. Is that what you're saying?
Yes. And I'm just confused on why it was that one. And then when I reworked another one, it still came out to 1/4. And I don't know. I just felt like it should have been simplified to 1/2. So I don't.
Let's see. Let me grab yours real quick here.
Because I wrote down the problem. It was e raised to the 2 minus 4x equals 8.
E to the 2 minus 4x equals 8.
Yes.
Okay, so we take the natural log of both sides, which gives us this. A little bit of rearranging gives us 4x equals 2 minus natural log 8.
Correct.
So x equals 2 minus ln 8/4. So it's because you could write this like this. Or you could write it like,
because it had the answer as 1/4 parentheses 2 minus ln 8.
Yes. You can only get 1/2 from this first portion here, the 2 divided by 4, if you break this up. Since this natural log of 8 does not have a 2 in front of it.
Right. So why wouldn't the number that's 1/4, why wouldn't it be 1/2?
It wouldn't be 1/2 because, so I divided everything by 4 here, right? So you have 2 minus natural log 8/4. So you could bring the 1/4 in front, or if you were to multiply it out, you could.
I see what you're saying. Okay, I got it. That was a brain. I don't know, that was a moment. Okay.
Does that make sense?
Yes, it does, because the 2 is really not by itself; it's connected.
Yes, exactly.
Right?
Yes.
Okay,
Yes.
Okay. That was my issue, because I did like try the other problems, and I'm just like, why am I keep messing up? But okay, I have it now. Thank you.
Yeah, no problem. By 5 in the beginning. What do you mean? In this problem? So is this what you were talking about? Well, we don't want to divide by 5, right? Since we're trying to solve for our x here. We could divide everything by 3 at the beginning. Well, we could divide everything by 3 starting at this step. But it's often simplest just to wait until the very end to carry out our division. Usually we want to go ahead and get, it's usually best to go ahead and isolate our x first. Does that make sense? Awesome. Let's see. Let's go through, yeah, we should have, maybe not. There's a nice example of using these laws of logarithms to expand a logarithm. I leave that as an exercise for the reader, as the textbook perhaps likes to say, or as is the meme in the math community. The last thing I want to touch on for logarithms is just that we have this change of base formula. Very nice, very versatile. This is a very simple, elegant way of entering a logarithm with some arbitrary base into your calculator. Some of us may have calculators that have some arbitrary base mechanism that's very easy to access. But some of us, like myself, have an older calculator, and it's not as easy to type in an arbitrary logarithm in there. The idea here is just log base b of x is equal to log of x divided by log of b. We could write this also using the common logarithm, by the way. We could write this as, say, log of x over log of b. This is also fine. This is true for any arbitrary logarithmic base. And this is mostly used for inserting a logarithm into a calculator. An example of this is that log base 8 of 5 is equal to natural log of 5 divided by natural log of 8. Or log of 5 divided by log of 8. Or, this could be anything. Log base 2 of 5 divided by log base 2 of 8. As long as the base in the numerator and denominator match, this is true. Does that make sense? Yes. Okay. And we can shift the graphs of these functions in the same way that we shift the graphs of other functions, really. We need to somewhat swiftly talk about inverse exponential, or the inverse trigonometric functions. Let me see. Is there a nice table with all of them? There's not. We only need 3 of them. We only need inverse sine, inverse cosine, and inverse tangent. And then we need to move on to 2.1, wherein we will discuss the tangent problem, not related to the trigonometric function, at least prima facie, not related to the trigonometric function. Let me see where we should start here. I suppose I should start right here. We have the inverse sine function. Sine inverse of x is equal to y. If and only if sine of y is equal to x, and y is between negative pi over 2 and positive pi over 2. So this means that the inverse sine function can only spit out angle values that are between negative pi over 2 and positive pi over 2. Does that make sense? The inverse sine function has a domain from negative 1 to 1 and a range from negative pi over 2 to pi over 2. This is because we have to restrict the domain of the sine function in order to define an inverse function for it, because otherwise these functions oscillate forever, right? Perhaps this is coming back into our memory from 172. And what was that?
Sorry, in this term, sine is there's sine, cosine, tangent. Sine is x, cosine is y, and then tangent is x over y.
You have it reversed.
All right.
We're going to get into, we don't need to worry too much about that at the moment.
All right.
We don't need to worry about circle too much at the moment. And of course, the inverse sine function and the sine function cancel one another. If I take the inverse sine of a sine function and vice versa, they undo one another. Does that make sense?
Yes.
That's basically the idea of these cancellation equations. Same stuff goes for the cosine function, except the cosine function is slightly different, or the arc cosine function, the inverse cosine function. Cosine inverse of y, cosine inverse of x is equal to y if and only if cosine of y is equal to x, and y is between 0 and pi. This is telling you that for the inverse cosine function, the domain, so the acceptable inputs for this function are going to be between 0 and 1, or rather negative 1 and 1, sorry. The range of the inverse cosine function is going to be 0 to pi. And again, the cosine function and the inverse cosine function undo one another. The inverse, also we're going to get different notations for these in a second. The last of the inverse trig functions is the inverse tangent function. Okay, I'm just going to copy the passage here. The tangent function can be made one-to-one, and the whole point of restricting these domains and ranges is these functions oscillate, so we have to restrict their domains and ranges in order to define an inverse function. Otherwise, they wouldn't pass the horizontal line test. There's a lot of good reading involved for about these things in the text as well. And if you need some extra review on that, I have some good 172. I can link you to the 172 text. That's free. The tangent. So the idea of the arctangent or the inverse tangent function here is that the arctangent or inverse tangent function can spit out anything between negative pi over 2 and positive pi over 2. But this function actually has a domain that is all real numbers. The domain of this function is all real numbers, and its range is negative pi over 2 to positive pi over 2, except these are not included, unlike with the sine function. And just to get a separate notation here, sine inverse of x is often denoted arcsine of x. Cosine inverse of x is often denoted arc cosine of x. And tangent inverse of x is often denoted arc tan of x. Does this make sense? Okay. All right. Are we ready for 2.1 for the real calculus stuff? Time to calculize. Extremely yes. So, also, I think it's on page 70 of the textbook. It's, I think it's at the end of this section. It's at the end of chapter 1. And that's totally fine. Let me really quickly grab a link for you real quick. This is a link to a free open source textbook covering all pre-calc stuff. The pre-calc 2 or math 172 stuff starts at chapter 5. Talking about inverse trigonometric functions, that's in 6.3. That's in so inverse trig functions are 6.3 there, as you can see in those table of contents. So I highly recommend also looking at the end of chapter 1. There is a section called How to Solve It, or rather, sorry, I accidentally scrolled past it. It's adapted from a book called How to Solve It, at least. It's called Principles of Problem Solving. Very, very good read on just generically how to solve a problem. So I highly recommend reading that. It will help to improve your mathematical maturity, as they say. Highly, highly encourage you to read those Principles of Problem Solving. All right, so we are on to section 2.1. 2.1. The tangent and velocity problems. The tangent problem. Are you excited? What does the word tangent mean? What does this mean?
Doesn't it mean like intersection?
Close. Also close, Sylvester. This comes from Sylvester, you're the language nerd here. You should know this. This is Latin. Okay. Previously in math, we've discussed lines that are tangent to circles, right? That touch circles at exactly one point. And that's actually the idea that we're going to get at here. This comes from a Latin word, tangens, meaning touching. So if we think of a tangent to a curve, we're thinking of a line that touches the curve at exactly one point, right? And if a line touches a curve at exactly one point, then it has to be following the same direction as the curve at that point. Do we agree? Yes. So, for instance, let me grab some screenshots here. Excellent pictures. One thing I really like about this text is there's some really good pictures. At least as an instructor, I like the pictures. Maybe as a student, you might not appreciate the pictures as much. I like these a lot. So here are two examples. You love them? Okay. For figure A here, we have a circle with a line that intersects this at exactly one point, right? For figure B, we have a line that appears to be tangent at this curve at a point. Although, because of the nature of the curve, this tangent line at the defined point P has to necessarily intersect that curve twice, right? So our definition of a tangent can no longer simply be that the line only intersects the curve at one point, because this line is touching this curve ostensibly at exactly one point, right? The idea here was to have this line touch this curve at one point. However, because the curve goes upwards, it has to intersect it twice here. Does that make sense? Am I talking nonsense? Okay. Sometimes I get real scared. Let's look at an example. I need a screenshot here. There we go. Let's find an equation of the tangent line to the parabola y equals x squared at the point 1, 1. How should we do this? This seems to be pretty difficult, right? The difficulty here is that I only know one point on this line, but how many points do I need in order to compute a slope of a line? I need 2 points, right? So I could find the equation of this line as soon as I knew its slope, right? But currently I don't really have the tools to find the slope of this line. So what we're going to do is we're going to choose a nearby point. We're going to choose a point that's pretty close, and we're going to approximate the slope of this line. For instance, and I suppose we need to choose a point that is on this parabola. Okay, we're going to choose a nearby point on this parabola to approximate the slope of this line. We're not just going to choose any arbitrary point. So for instance, if we chose the x value, well, 1.5, because the x value of 1.5 is pretty close to 1, what's my y value going to be? Well, this point has to be on the parabola. I need to choose another point on the parabola that's nearby. So I need to plug this into y equals x squared. I left that bit of information out the first time I said it, so that's totally okay, right? So I get that y is 2.25, right? So if I want to find the slope of this line with these 2 points, then I would do y2 minus y1 over x2 minus x1. Do we agree? So this gives me 1.25 divided by 0.5. And this is 2.5. Now, this is just an approximation of the slope, right? This isn't actually the slope of the line that is tangent to this parabola. In fact, this is what is called the slope of what's called a secant line. This line intersects the curve twice, right? We have 2 points on this curve. And also, let me grab a picture of what we're looking at here. Trying to find the slope of the line tangent. We're trying to find the slope of this red line, right? We chose a second point, x squared, right? Where x squared is my y value. And we found the slope of that secant line, which ended up being 2.5 in our case, which is a little bit steeper than this red line, right? In this picture. The red line, it's kind of giving a little bit away here. So what we want to do here is, or rather, let me ask a question. Sorry, getting ahead of myself. How do you think I can end up getting the slope of this red line? I currently have an approximation of it. I could have done 1.1. Yeah, good idea. I could have, good idea. So we're saying, let's try an x value of 1.1 because the x value 1.1 is closer to an x value of 1. Okay, I like that idea. If x is 1.1, then y is 1.1 squared, right? And this is what? 1.21. So my slope is 1.21 minus 1 over 1.1 minus 1. This is 0.21 divided by 0.1. And this is 2.1. And this is closer. Yeah. This is still an approximation, right? What could I do to what can I do to better approximate this? $1.0001. Yeah, I could use a number that's even closer to 1, right? The idea here being I'm taking this other point, Q, that I'm choosing, and I am sliding this point closer and closer towards P, right? Do we agree that that's what we're doing here? We're essentially pulling this point closer and closer towards the point P. What if I did this from the other side? So if I were to keep doing that, let me try that again. If I were to keep doing that a few more times, I would get slopes that are closer and closer and closer to a certain number, right? Now I could also approach this point P from the other side, right? I could say my point Q is somewhere over here, right? Oh, awesome. Congratulations. That's awesome. That's great news. Awesome. Keep up the good work. So I could have approached this from the other way, right? I could have drawn a line that runs these 2 points where my point Q is on the dot that I just drew, right? Which would instead cause this slope to be an under approximation of the red slope. Does that make sense? And then, as the points get closer and closer and closer together, right? Well, as those points get closer, my slope would get closer and closer to the slope of the red line, right? For instance, I could have said that x was 0.5. And if I chose for x to be 0.5, y would be 0.5 squared, which is 0.25, right? And I could find the slope this way. This would be 0.25 minus 1 over 0.5 minus 1. This would be negative 0.75 divided by negative 0.5, which would be positive 1.5. And then I could say choose x equals 0.9 and 0.99 and so on, right? Until I got a chart looking like this chart. The one that I'm about to paste. Notice here that these slope values seem to be getting closer and closer to a certain number as this x value gets really close to 1, right? Do we see that as I let this x value get really, really close to 1, these slope numbers are getting really, really close to a certain number? What does this suggest that the slope of this line should be? At this point, we can take an educated guess. 2. We can take an educated guess here that the slope of this line is probably 2, right? The slope of this tangent line is probably 2. And if I know the slope of the line, then I can find the equation of the line at that point, right? If I know that m is 2 and I want this line to pass through the point 1, 1, I can plug this into point slope form. Y minus 1 is equal to 2 times x minus 1. Oh, I didn't close my parentheses. Adding 1 to both sides, I get that y is 2x minus 1. And this is the slope of this tangent line. Does this make sense? So we say here that the slope of the tangent line is the limit of the slopes of these secant lines. And we use a certain notation to express that. I'm going to copy and paste what they have right here, just because they have a nice little paragraph on it. It's not really a paragraph, it's a sentence. Now, just to explain where x squared minus 1 and x are coming from, it's from this point being the point x comma x squared. Okay? It's from the second point being the point x squared. Since the y values of this second point are all x squared, right? So y2 minus 1, or y2 minus y1 is x squared minus 1. x2 minus x1 is x minus 1 in this over here. So because the slope of the tangent line is the limit of the slopes of the secant lines, and we had defined points P and Q. I'm going to copy and paste this graph down here. We say the limit as Q approaches P, so the limit as this arbitrary point that we defined on the parabola gets closer and closer to the point 1, 1 of the slope of the slope of the line between P and Q is equal to some number m. So in particular, the limit as our x value approaches 1, so the limit as the x value of this point gets closer to the x value of this point of the slope equation that we had set up is equal to 2. Does this make sense? The limit as x approaches 1, so the limit as our x values get closer and closer to 1 of this equation is equal to 2. Okay. And let's just look at some graphs of what this looks like here, of a bunch of different points P and Q. Oh, my window snipping tool somehow got in the way of itself. So on the top here, we have the point Q approaching the point P from the right. The point Q starts pretty far away and gets closer and closer. And notice how the slope of the blue line is approaching the slope of the red line, in that case, from above, right? And again, we could have chosen a point way over here on the left, right? And we would have ended up if we had chosen a point far enough on the left, we would have had a slope with a negative value, right? But as this point Q gets closer and closer and closer to the point P, where essentially these points become indistinguishable from one another eventually, right? At that point, we've reached a limiting value, which in this case is 2. Does this make sense? This is a bit of an out there concept, right? This is what's called the tangent problem. And this is a relatively informal definition or informal treatment of limits so far. So let's move on to the velocity problem. This is a related problem. And these are going to tie into the same concept. So, let's just read out this paragraph together because I like this. I like this example. This is actually the thing that's made me start thinking about calculus. Kind of was driving my car. I like this paragraph a lot. If you watch the speedometer of a car as you drive in city traffic, you'll see that the speed doesn't stay the same for very long. That means that the velocity of the car is not constant, right? We can assume from watching the speedometer that the car has a definite velocity at every moment. But how do we define this instantaneous, quote unquote, velocity? Let's consider the velocity problem. Find the instantaneous velocity of an object moving along a straight path at a specific time if the position of the object at any time is known. In the next example, we're going to investigate the velocity of a falling ball. Through experiments carried out 4 centuries ago, Galileo discovered that the distance fallen by any freely falling body is proportional to the square of the time that it's been falling, which, of course, this ignores air resistance. If the distance fallen after t seconds is denoted s of t and measured in meters, then, at the Earth's surface, Galileo's observation is expressed by the equation 4.9 t squared. Does this make sense so far? Do we understand this idea that something that's moving can have a velocity at a certain moment, right? That it can have an instantaneous velocity? Let's look at this example. Suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Find the velocity of the ball after 5 seconds. So, the difficulty here of finding the velocity of the ball lies in the fact that we're dealing with a single instant of time. There's no time interval here. Have we found the average velocity of something falling before in a previous class? Do you recall ever finding the something's average velocity across a time interval?
It was just like the mean, right? I remember doing it. I don't really remember how it was done.
Okay. So the way that we find average velocity, and this is not the same as instantaneous velocity, but it will hopefully help us out. Average velocity is just change in position over change in time. Or change in position over time elapsed, or change in time. Does that make sense? I can tell you your average speed during a drive if you tell me how far you drove and how long you drove for, right? Does that make sense?
Makes sense.
Yeah, that's so that's the basic idea here. If I know how long you drove for and how far you drove, I can tell you how fast you drove on average across that time interval. So let's try creating some arbitrary interval. Let's say a relatively small interval. We want to find the velocity of the ball after 5 seconds, right? Let's try finding the average velocity of the ball from, say, t equals 5 to t equals 5.1 seconds. So my average velocity here is s of, and I suppose I should rewrite this equation that we had. The equation that we just had above us was s of t equals 4.9 t squared, right? So my average velocity is change in position over change in time. So my change in position is s of 5.1 minus s of 5. And my change in time is 5.1 minus 5. Do we agree that this is my average velocity from 5 to 5.1 seconds? S of 5.1 is 4.9 times 5.1 squared. And this is minus 4.9 times 5 squared over 0.1. 5.1 minus 5 is 0.1. And if we throw this into a calculator, what do we get? .49. Very good. And this is in terms of meters per second. Yep. Now, we can shorten this time interval. And if we shorten this time interval, that should get us closer and closer to the instantaneous velocity of this object. Do we agree?
Yes.
So if instead of looking from time 5 seconds to 5.1 seconds, I look, for instance, time 5 seconds to t equals 5.05. Oh yeah, we could go that far out too, right? We could go. Yeah, that's a lot of zeros. Maybe we'll go as far as maybe this one. I don't feel like writing more zeros than this. If we make the point being, if we make this time interval really small, we should get pretty close to the instantaneous velocity. Well, let's see. Let's plug this in. We'd have what? 4.9 times 5.00001 squared minus 4.9 times 5 squared over 0.00001. Let's crunch the numbers here. 4.9 times 5.00001 squared minus 4.9 times 25. All of this divided by 0.00001. I'm getting that this is about 49.0000049 approximately. So if we had chosen a few more gradual time intervals, what we would have gotten was this. You love these? We would have seen here that this average velocity is getting closer and closer to what? What do we think this average velocity is getting closer and closer to?
It looks like 50. Not 50.
It looks like 49. Right? It looks like this is getting closer and closer to 49. So we can make an educated guess here that the instantaneous velocity of this object after 5 seconds is 49 meters per second. Now, we're going to I wrote too many things. Yes, there we go. Instantaneous velocity is 49 meters per second. We can make an educated guess here as it seems as if we're approaching some limiting value, right? And if we made this interval arbitrarily small, we could see that it continues to get closer and closer to 49. These calculations seem to be oddly similar to something else that we looked at before. Do we recall the difference quotient? We're getting there. We're getting to the slope of the tangent line. We're getting there. We have to establish limits a little bit more firmly to very firmly get to the slope of the tangent line. But what we found here is the slope of a tangent line. Yeah, at a single point. Do we recall the difference quotient from before? This f of x plus h minus f of x all over h. It seems like we're adding an arbitrary length of time to this 5 seconds, right? So let me gather my thoughts in my mind palace here for a second. Essentially, we have 2 points, right? The one point that we have solidly is the point 5, whatever 4.9 times 5 squared is, right? This is one of our points that we've used consistently, right? 4.9 times 5 squared corresponds to the distance traveled after 5 seconds. And then we can establish another point Q, which is 5 plus some h amount of time, right? Comma, 4.9 times 5 plus h squared. So this means that the slope of this secant line, MPQ, would be 4.9 times 5 plus h squared minus 4.9 times 5 squared all over 5 plus h minus 5. Notice that the bottom simplifies here to just h. And this would be f of x plus h minus f of x all over h, right? What do you think we have to do with this h in order to get the slope of the tangent line from this? Where this h is some number that I'm adding to 5, right? This h is essentially how long this time interval is. How long should the time interval be at a single point?
It would just be that time. It wouldn't be an interval, right?
So yeah, the interval at a single point should be 0, right? So essentially, in order to find the slope of this tangent line from the slope of the secant line, the idea is that we're going to have to let this h value get closer and closer to 0. Do you agree?
Yes.
Now, the only issue with that is we can't plug 0 in directly, can we? Because then we'd be dividing by 0. So we're going to have to look at how to do this. I need 1 second, please. I'm going to be right back. Just 1 second. All right, I'm back. So if 2.1 seemed a little bit confusing, that's okay. Because 2.1 was largely motivation for section 2.2 and beyond. So let's take a peek at section 2.2. New section group, and this one is named 2.2. So we are going to continue to discuss this idea of a limit, perhaps a little bit more rigorously now. Really, the truly rigorous definition of a limit is going to be in 2.4, which I am explicitly going to omit from this course. I don't see a lot of value in going over 2.4, but I do encourage us to look at 2.4. So, in order to investigate this idea of a limit, let's investigate the behavior of a certain function. Let's investigate the behavior of the function f defined by x minus 1 divided by x squared minus 1 for values of x that are near 1. This following table gives values of f of x for values of x that are close to 1 but not equal to 1. So it starts out by plugging in values of x that are less than 1 into this function. So these values are all less than 1. And notice that as we get further down the table, these x values are getting closer to 1. And in the second column here, we have the output values that correspond to each of these input values. So if you plug 0.5 into this function, you get 0.6666 repeating. If you plug 0.9 in, you get 0.526316, and so on down this table. Do these y values seem to be approaching something?
.5.
0.5, I'd say. In this third column here, we're plugging in values of x that are greater than 1, starting far away and getting closer and closer. So if you plug 1.5 into this function, you get 0.4, and so on. So these x values are getting closer and closer to 1, but from the right instead. And what do my y values seem to be approaching here?
Also 0.5.
Also 0.5, right? Yeah. So we could blah, 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 investigate the graph of this, right? We'll do that in a second. It appears here like we can make the values of f of x as close to 0.5 as we want, as long as we make these x values close enough to 1. Do you agree? Do you agree that as long as these x values get close enough to 1, I can make those y values get as close to 0.5 as I want? So we expressed this idea. Did you see my Final Fantasy XIV background? You probably saw my Final Fantasy XIV wallpaper just then. Let me grab a graph here to show you this before we get some notation for our limit. So this is the graph of x minus x squared over 1. Now notice that in this graph, there's actually going to be a hole at x equals 1, right? There's a hole at x equals 1 in this graph due to dividing by x squared minus 1, which is the same as x minus 1 times x plus 1, right? There's a removable discontinuity here. So a function value here is not defined. Although I can get, you see that as I approach that x value from either side, that my y values get really, really close to 1/2. We can express this notationally, and well, verbally, we can express this as the limit of the function f of x equals, let me write this on another line, x minus 1 over x squared minus 1. As x approaches 1, what would you say that is? What would you say the limit of this function is as x approaches 1? 0.5. Correct. And we express this notationally as in this way. Well, let me choose a different color just for the contrast here. I'll go with red. Orange is too bright. The limit as x approaches 1 of x minus 1 divided by x squared minus 1 is equal to 0.5. Does this make sense? This is equivalent to the words above it. Is this okay? So let's get a nice boxed in definition of the limit. How about it? It's about time, right? This is what we call the intuitive definition of a limit. Suppose that f of x is defined when x is near the number a. This means that f is defined on some open interval that contains a, except possibly at a itself. So this is just saying that the function is defined close to this x value, although it does not have to be defined at the x value that we're getting closer to. Does that make sense? As in this case, I wanted to paste the graph down here. As in the case that we just looked at, we actually have a hole at the x value itself. So it's okay if the function is not defined at the x value itself, as long as it's defined around that x value. Then we write that the limit of f of x as x approaches a equals L if we can make the values of f of x arbitrarily close to L. That means as close to L as we like, by restricting x to be sufficiently close to a on either side of a, but not equal to a. Does this definition of a limit make sense? This is essentially saying that the values of f of x of the function approach L as x approaches a. Or, in other words, that the values of f of x get closer and closer to L as x gets closer and closer to a from either side. But x is without x being equal to a. So this is just reasserting that this function does not need to have a defined function value at this x value that we're trying to approach. In fact, often we're going to look at limits where there is no defined x value at the x value that we're trying to approach. There's no defined point there. Although there could be. So are we ready to look at evaluating a limit with limit notation here? Yeah. What do we say? Yeah? All right. Let's look at this example. Oh, started clipping it too early. There we go. Let's estimate the value of the limit as t approaches 0 of the square root of t squared plus 9 minus 3 all over t squared. We could try just plugging numbers into this, right? If we plugged 1 into this, for instance, we would get about 0.1622. And let me just give us a table with a bunch of values. We're going to have to manually plug some of these in on our homework. and on our lab. But I figure for the sake of brevity here, I'll just give the table where they've already plugged in plus or minus 1. Notice that it doesn't matter whether it's plus or minus here because the number is always getting squared no matter where we're plugging it in, right? So we're going to get the same result for plus or minus any number. What do we think that the limit is based on this table?
1.7 maybe, or 0.17.
Yeah, 0.17, or we think that this might be approaching, maybe we think that the limit here is about 1/6. This appears to be about 1/6, right? 0.16666, which is about 1/6, right? So it appears reasonable that this might be approaching this value of 1/6. Do we agree?
Yes.
What if we chose, okay, so if we're trying to get t to be closer and closer to 0, right? What if we chose a value that's really, really close to 0? What if we plug in 0. 0, 0, 0, 0, 0, 0, 1. What if we plug this into the function? What do we get? Plug this into the function for us. What does this give us if I plug this into this function? Gives us something that's really close to 0, doesn't it? If I plug this into the function, I get something that's really, really close to 0. So is my limit equal to 0? Instead of 1/6? No, so what's happening here is the limit of this actually is 1/6. However, whenever you plug in a sufficiently small number to this t, the square root of t squared plus 9 gets really, really close to 3, right? As we plug in a smaller and smaller number for t, the square root of t squared plus 9 gets really, really close to 3. It starts getting so close to 3 that the calculator just says that it's 3. And so as a result, the calculator actually starts spitting out something false because the calculator can only operate to a certain level of precision. Does that make sense? Essentially, the calculator ends up having a rounding error here. The limit does end up being about 1/6. And this is also why it's important for us to eventually find another way of evaluating these limits that doesn't just involve plugging a bunch of numbers in, right? Let's see. Let's look at another one here. That's the value of the limit as x approaches 0 of sine of x divided by x. Now, you can't just plug 0 into this function because it's not defined when x is equal to 0, right? Because we'd be dividing by 0. We could create a table here, right? We could also go to Desmos and try graphing this. Maybe we'll go to Desmos and we'll try graphing this, and we'll see how this function behaves as it gets close to 0, as x gets close to 0. Let me share a Desmos tab here. I wish there were a way to share my Desmos easier without like unsharing and then resharing. Okay, I've graphed our function. Notice that, oh, where were we? At x equals 0, our function is undefined, right? But what's this y value really close to? What y value is this really close to?
1.
It's really close to 1, right? Notice that as we approach this from the right, these y values they actually get so close to 1 that Desmos actually just says that it's 1 at a certain point, right? That's how close this is to 1. So we could probably guess reasonably that the limit of sine of x divided by x as x approaches 0 is equal to 1. Do we agree?
Yes.
So let's go back here. Math 271. So this is equal to 1. This guess actually is correct. And we're going to prove that in chapter 3. Cool. Let's see. Do we have time to discuss one-sided limits? I suppose we do have time to... maybe we don't have time really to discuss one-sided limits. I think that we should probably pick up with one-sided limits tomorrow. Right, because we only have a couple of minutes left. I'm the teacher. Well, we would have to go through an entire definition, right? I think it's probably best for us to leave this this next definition until tomorrow, right? We've kind of done a lot today, and we've done a lot that's probably thoroughly confusing. What do you think? Definitely. All right. You felt this is the best class so far? Cool. This is only my second time teaching calculus. And it's my first time teaching it online from the beginning. So I'm trying my best over here. Monday and Tuesday were rough. The beginnings here of this limit stuff are a little bit difficult to grasp because the beginnings of the limit stuff are a little bit hand wavy, right? We don't have too many hard rules yet for this stuff, do we? We are going to develop some more hard rules as we go along. Right now, we're just trying to get an intuitive understanding of what a limit is. Does that make sense? Does it make sense why we haven't gotten any like real mathy math, it feels like? Oh, awesome. Yeah, eventually we're going to, tomorrow, in fact, we're going to get into limit laws that are going to help us calculate limits. So before I dismiss us for the night, do we have any questions that I can answer? Any fears that I can help us be unfearful of?
Nothing comes to mind.
Something coming to your good. All right. So I successfully recorded today. There's a recording of all of it. It's all there. I'm proud of myself. No mess ups. Not today. So as usual, if you have a question, please send me an email. Please come to my office hours from 2 to 3. Whenever you come to my office hours, I'll probably be on my office hours on my iPad upstairs or something. Just say something. You can just say something out loud, and I should hear it through the iPad speakers. Or you can just type something, and I should hear that notification as well. So yeah, please send me any questions that you have, or stop by office hours. Hard night for you, but it was informative. Yeah, and if you need any additional resources or anything, I can also try to find those for us as well. Just like I posted that link to the full 172 textbook earlier. So if we need anything like that, please let me know, and I'll do my best to accommodate here. You can also, if you have any questions about the or something doesn't make sense, you can feel free to just like send me a screenshot or send me like, hey, I'm having trouble on this problem on this homework, something along those lines. Remember, the course entry assignment is due tonight, and the homeworks, all of the homeworks for this week, everything through 2.3, which is being covered tomorrow, are due on Saturday, and the lab is due on Sunday. To access the lab, the coursework section, you can either upload your answers there, or you can send your answers to me via email. You can send the document to me via email. You can either type it up, or you can like do it on paper and take a picture of it and send it to me. That's also fine. A lot of people really like working out on paper. So same goes for you for the lab. Yes, for the lab. Yeah. The same idea goes for if you are working out a problem and you get stuck, you can feel free to like take a picture of your work and say, hey, I got this far in the problem. Where did I go wrong? Or something like that, right? And I can try to help you from there. So please let me know if there's any way in which I can help. And also, please have a great rest of your night.
You too.
I'm gonna go eat big dinner. We're actually cooking tonight. We're being good. Have a good one, everyone.